A guy trained a transformer model to predict his own blood sugar for the next 2 hours, and it runs on his phone. A guy trained a transformer model to predict his own blood sugar for the next 2 hours, and it runs on his phone. The project is called T1DMI. It is open source under the MIT license, and the creator has been working on it since March. This is not a medical device, but it is a genuinely clever piece of AI engineering applied to a real personal health problem. So what is T1DMI? It is an encoder-only transformer that forecasts blood glucose for type 1 diabetes. It reads 3 signals that a phone can actually observe: continuous glucose monitor data, logged carbohydrate intake, and logged insulin, and it returns the next 2 hours as a fan of 7 quantiles, so every forecast carries its own uncertainty built right in. The model does not predict in standard milligrams per deciliter. Instead, it uses something called the Kovachev risk transform, which warps the glucose axis to stretch the low range and compress the high range. That means the same absolute error is worth several times more loss at 60 milligrams per deciliter than at 300. The whole point is that hypoglycemia matters more, and the math encodes that without any special rewinding. The architecture is where things get really interesting. 6 consecutive 5-minute samples get collapsed into a single 30-minute token. A pre-normalized transformer stack then attends over those tokens using rotary position embeddings, QK normalization, and a learned per head ally by bias, so each attention head naturally settles on a different temporal scale. The attention is bidirectional inside the context and inside the prediction horizon. But the past context is blocked from reading the future, so no future information leaks backward. The model uses 2 output heads. The first head predicts glucose and emits low-frequency coefficients per patch rather than one value per time step. That means a jagged step-to-step zigzag is unrepresentable by design. The median is projected onto a low-frequency basis spanning the whole horizon, which smooths across patch seams and bounds the drift away from the last observed reading. At initialization, the forecast is just a flat persistence line. The second head is a time-of-day probe. It classifies each prediction patch into one of 12 2-hour bins. There is no clock input, so the model has to infer the hour from the glucose trajectory alone. It never touches the glucose forecast, but its gradient reaches the shared trunk, which pushes the same representations. The glucose head reads to encode circadian phase. The training pipeline is thorough. The model is pre-trained on synthetic traces from the T1DMSIM behavioral simulator, then fine-tuned on real continuous glucose monitor cohorts. The creator trained 4 model classes, from a tiny 38,000 parameter nano model up to a 17 million parameter large model. Pre-training the largest model took about 48 hours on a single GPU. Fine-tuning took less than 10 minutes. The optimizer setup is unusual: muon for every parameter with 2 or more dimensions, and atom W for the one-dimensional ones like norm scales and biases. The loss combines pinball loss over all 7 quantile levels with dilate loss on the median, which is a shape term built from soft dynamic time warping. A forecast that predicts the right glucose excursion a step early is not punished as though it predicted the wrong excursion. The 2 loss terms are fused by learned uncertainty weights that the model tunes during training. The model is patient agnostic, meaning there is no learned per patient vector, so identity is whatever the 8 to 24-hour context window implies. Here is what makes this really impressive. The trained model exports to Execu Torch or LiteRT and runs on-device in a companion Android app called T1DMDroid. The creator showed predictions running live on his phone, switching between different models on demand. It works on both CPU in full 32-bit precision and GPU using Vulkan with half precision. There is even a bolus advisor feature that runs the model multiple times to compute insulin dosage given a target blood sugar level. The model requires announced carbohydrate and insulin data to make predictions, which makes sense because those are the inputs it was trained on. The creator also mentioned that the model always requires announced carbs and insulin, and would be better if it could predict without them, which is an area for future improvement. The results are published in the repository. On cross-patient evaluation with patients the model never saw during fine-tuning, the medium model with 2 million parameters achieved the best accuracy. But here is the surprising finding: accuracy is flat across model capacity. Across a 450 times spread in parameters, the held-out numbers sit within 1.2 milligrams per deciliter of each other at 60 minutes. And the tiny 38,000 parameter model is within 1.3 of the best at 30 minutes. The fine-tuning is what moves the needle, not the model size. The simulator-only models without any real data fine-tuning are noticeably worse, which shows that the domain gap between synthetic and real data is real. Clark-era grid analysis puts 91 to 92% of predictions in clinical zone A, which is the safest zone. The Reddit community had some strong opinions. The top comments asked why use a big transformer for this, with several commenters wondering if a simpler model like SARA-Max or an LSTM would have done just as well. The creator replied that so far he has not tested against other models, and this is a side project to improve his own blood glucose metrics. One commenter pointed out that 16 layers with 16 heads and 17 million parameters is actually pretty skinny for a transformer. Another raised overfitting concerns, asking if the predictions versus true values were from the training set. The creator confirmed he is evaluating the model on his own personal data right now. Someone else asked about comparing it to CGM-Former or simpler RNN models. And another commenter wondered how the model could ever predict without announced carbs. The creator's response was that it would use previous patterns to guess when a person would eat and how much insulin they would take. And a commenter noted the strange lack of upvotes despite the project being genuinely impressive. So where does this leave us? T1DMI is a research artifact, not a medical device, and the README makes that very clear with a big caution block. It is not clinically validated and has no regulatory clearance, but it is a fascinating demonstration of what modern transformer models can do when applied to a real-world signal processing problem. The RISC-based formulation is genuinely clever, the on-device deployment is impressive. And the fact that it is fully open source under the MIT license means anyone can dig into the code, try the models, and build on top of it. The repository is at /0xdeadf1sh/t1dmi on GitHub. If you are into diabetes technology, transformer models, or just cool side projects that solve real problems, this is worth a look. If you found this interesting, check out the GitHub repo and try the models yourself. And if you have thoughts on whether a transformer is the right tool for this job, let me know in the comments. Thanks for watching.